Okay. Dun, dun, dun. 1 week from yesterday, exam 1 is happening. That exam is going to cover everything that I still haven't taught you this week, which is the way I prefer to do it. I don't want to teach you something and then teach you something new and then give you an exam like a week later. I want you to just get this material figured out, rip it off like a Band-Aid, and then move on to something new. So that's the way I'll operate. So a week from yesterday will be exam 1 in the evening. You'll have a formal exam review will be in your discussions on Friday. So those that probably want to attend. Those of you guys just kind of, you're 1 week out, you want to kind of get the ball rolling on some studying. I'm just going to point out a few things real quick. So Canvas here, link to the lecture videos if you didn't get them. There's also discussion videos. If you left discussion maybe more confused than you entered, think maybe I should listen to a solution again. One of our TAs, Michael, has been recording what he writes down and then saving that. Those are a YouTube link, so you can check that out. What else do we have? We got office hours every day of the week. TAs or I are in there, well, save for the weekends. And then we've got sample exams and sample exam solutions. Those of you guys who are real go-getters, you might have jumped into these sample exams. Okay, my mouse is betraying me. And midterm 1, I've got a couple of them already up there. My recommendation at this point is that use these as a diagnostic to see how good you actually understand material. Right? Like we are pretty good at solving questions if I solve them for you, if your TA solves them for you, and if you have the solution manual to the homework, right? But when left on your own, maybe see how good you are. So these problems you can check out, sit down and try to solve them, and it'll be a reasonable assessment of how good you are. Our exam is going to be a little different than what's up here for these sample exams. These have some short answer and then some full-length questions. Ours is going to be like 3 homework problems. So 3 kind of full-length questions, 90 minutes, so 30 minutes per. I do got to go in here and tune these up a little bit. Midterm 1 has traditionally been through the next chapter, but I've kind of scooted everything forward to break it up a little bit more evenly. So I'm rewriting some of the solutions so it doesn't use work energy if you've jumped in there already and you see something you don't recognize. And I'll put a little note here like, hey, don't do that problem. And then I'll update the solutions as well. I've already started that too, so that's kind of on its way. Oh, man. And we're struggling. Okay. The last thing we can see, equation sheet. This is going to be printed on your exam, so you'll have this to work with while you're taking the exam. So not a bad idea to take a look at that early and be prepared to use that. Oh my God. Okay. Last thing. So I've got this little module for the midterm review that you see up there. That's what your TAs are going to cover, those slides in discussion on Friday. And then also I have the request for an alternate exam time. I've heard from about 10 of you. 3 of you are troublemakers, don't fit into my time slot, so I'm still waiting for the dust to settle before I figure out what to do on that. That closes tomorrow. So if you have an exam conflict that you figured out on Thursday, tough luck, right? That's on you. I've given you 2 weeks to figure it out. So very generic exam. Get ready for it, okay? So do your homework problems, look at the quizzes, look at discussion problems. If you need some more stuff to look at, remember, all the video, there's video examples under all the lectures too, written from or recorded by another professor, so that's more problems you can see. So if you're struggling on a certain topic, take a look at those. And also, I suggest reading the examples in the book. They're super well written, and I think the flow of the problem solving is really good. So if you're struggling on a certain type of problem that you've learned by trying the practice exams, go back and look at those things for some extra help. Okay? Throwing out there any questions? Good. All right, on to the business then. If I can get this thing to work. That's my hamster. Totally normal stuff, guys. I mean, you come to engineering class, you hear about hamsters. Oh my God. All right. So last time we got together, we did F is equal to MA in Cartesian coordinates. We had X and Y lined up. Well, today we'll extend that to polar and normal tangential coordinate systems. Lucky for us, there's really not a whole lot of theory to go through here. We just need to take a little trip down memory lane to polar and NT. So for polar coordinates, well, what's going to be important? Writing our accelerations is what we're going to want to be able to do. So we've got r double dot minus r theta dot squared in the r direction plus r theta double dot plus 2 r dot theta dot in the theta direction. And nt, our velocity, our changing in velocity was our tangential component, and v squared over rho was our normal component. And maybe the one other thing we need is rho. So sometimes rho we could pick out. Maybe we were traveling a circular path. Our car was driving. Rho would just be the radius. Maybe I've got some function of x, y. We had an equation for rho. 1 plus the derivative of y with respect to x squared, all that to the 3/2 power, divided by the magnitude of the second derivative of y with respect to x. And we'll do one of those. Other than that, the mechanics of how we go about these problems is going to be the same. We're going to look at something. We're going to draw an FBD. I'm just going to draw one in here willy-nilly. Okay? This free body diagram is going to be equal to our kinetic diagram. So maybe this thing is on, draw a coordinate system in. This is my r direction. This is my theta direction. So if I'm looking at r and theta, I got my free body diagram side equal to my kinetic diagram side. Mass times acceleration in r. Mass times acceleration in theta. And all we're going to do is we're going to pull off components. Sum of forces in the r direction, sum of forces in the theta direction. The key is now that, hey, we're smart and we can figure out that I've got an expression for the acceleration in r. And I've got an expression for acceleration in theta. So we know something now that we can put to use to solve these problems. Exact same thing for nt, except I would have drawn an n and a t. But the same idea. So part of the trick for us is, well, what coordinate system is going to be the most beneficial? X, y, nt, polar. And then once we have that, then we're just writing sum of forces, drawing free body diagrams like you did in statics. All right, this is old news. I already talked about this. Acceleration in the R direction. They used capital R's, I used lowercase. Same thing. Just wanted to make things look a little confusing. There was a third dimension. If there was a z, there happened to be a z in this problem, that would just be out of the board. That one we don't have to worry about. That one gets a little gnarlier if you start working on spherical coordinates, and we'll do all that in advanced dynamics. So don't have to worry about that too much for now. So polar coordinates, maybe you're given a path where the radius is a function of position in angle. This is one of these things that's leading us towards polar coordinates. If I see things traveling circular paths, immediately I think polar coordinates. But the one gotcha maybe with the circular path is that NT is pretty good in circular paths as well, right? Because this is my radius rho. So maybe if the problem says, hey, I've got this car. I just changed this thing into a car. And it's traveling at 10 miles per hour. Tell me something about the normal force or the reaction force. Well, hey, because I'm given a velocity, even though it's traveling a circle, I think, you know what? NT is actually a good coordinate system to use because we've got velocity. And I already know something about velocity. But if you were given information a different way, hey, this little car is traveling a circular path, and it has an angular velocity omega and an angular acceleration alpha. Like, hey, this might be easier to use polar. Remember that omega is theta dot, alpha is theta double dot. So sometimes information we're being fed can make a coordinate system choice a little easier or a little harder. Certainly, solving these problems either way would be fine, but you just have to do a little bit of a conversion. If you were given angular velocities and you wanted linear, or if you were given the linear velocity and you want angular, you just got to rotate back and forth. Don't memorize these equations. Yeah, definitely not. So for this, there's just some other types of internal forces. I don't even know why they're on this screen. So gravitational force. This would be like a celestial gravitation. Here I've got the Earth and the Moon revolving around it. This force that acts between them. F is equal to the universal gravitational constant, some number that I don't know off the top of my head, not 9.81, times the mass of Earth times the mass of the Moon in this example, divided by the distance squared. And this happens, this force is acting in the negative u hat r direction. So forces between two bodies. A lot of times with these gravitational problems, they are in a circular path. So again, not an equation that you're going to need to remember. Electrostatic force, similar idea, different equation. You've got that pull between these two bodies. All right, let's get to some examples. This is my hamster Sprinkles. This was my hamster Sprinkles. He may still be alive, I don't know. My son liberated Sprinkles by leaving his cage door open, so Sprinkles he's moved on to a better place no matter what. But Sprinkles, Sprinkles was a runner. So like every night, he'd get out there and he'd haul, cruising. Oh, then he would stop. He'd turn his little legs off, and he would get zipped around his wheel. And you think you're watching Sprinkles, you're like, dude, do this 100 times a night. It's got to hurt. But it got me thinking. It thinks I'm really into hamster videos now. Okay. So, how fast does Sprinkles need to get his little legs going so that he can pull off a full pull, full loop-de-loop? That was the question I was thinking about. And hey, he's going to run, get his legs going super fast. And then, because he's a hamster, he hits the brakes. And his body is going to jump onto that wheel and then be spun around. So he's going to have some angular velocity that I think we should look into, try to figure it out. Do not play me more hamster videos. Okay. We'll pause that for now. Let's try to figure out what's going on. We got Sprinkles. So we got Sprinkles running super fast on this wheel. But I want to know what angular velocity. I want to find omega minimum. So find the angular velocity such that she doesn't fall. And I don't remember if it was a she or he. I didn't check. So find the minimum angular velocity so she doesn't fall at the top of the wheel. I'm going to ask for angular velocity because it's something that we're going to be able to play this video and kind of count to see if it does match what we think it should be. But if I said, what is the minimum velocity, all we're doing is linking up some angular velocity with some linear velocity, right? So, hey, my linear velocity is omega cross r, or omega times r. If we're not worried about figuring out the direction, we can just do that with our head, ourselves. So, but feeding you information for angular velocity, I think you should do this one in polar. Had I asked you for velocity, I'm probably thinking NT coordinates. So the way we start these problems, just like before, FBD. Here we're interested in Sprinkles. So this is my body. So we've got mg coming down. Sprinkles is stuck to the wheel that's spinning around. So we've got a frictional force between Sprinkles and the wheel. And then there's a normal force between Sprinkles and the wheel as well. So the wheel pushes back towards Sprinkles, and Sprinkles pushes back towards the wheel, right? That's our N. This one that I've got going up is actually acting on the wheel, so I'm just drawing it kind of for completeness. But it's certainly not acting on this particle. So, got my free body diagram. I want to set that equal to my kinetic diagram. For my kinetic diagram, here, this is the particle I'm interested in. This is mass times acceleration in the r direction. And then positive counterclockwise, mass times acceleration in theta. All right. We want to find when Sprinkles falls off. So she falls off when the normal force goes to 0. There's no longer contact between her feet and the edge of the wheel. But we'll include everything for now. So I got sum of forces in the radial direction. For my drawing, it's pointing up for now. Minus mg. My normal force acting on sprinkles is also pointing down. Minus n is equal to my kinetic diagram side in that same direction. Mass times acceleration in the radial. Because we're looking at the minimum when she loses contact, I'm going to let this n go to 0. All right. Well, this isn't too tough. What is acceleration in the radial direction? R double dot minus R theta dot squared. So if she's traveling in this circular path around and around and around this wheel, she's not changing her radial position until she flops off. But for now, she's traveling around and around and around. So we're not accelerating in the radial or changing our radius, our radial position. So we've got here minus mg is equal to mass times another minus sign r theta dot squared. The negative signs and the masses will cancel. Theta dot squared is equal to g over r, and I'll just square root that right away. Okay, so this is a 6-inch wheel. So my radius is 3 inches, or 1/4 of a foot. My g is gravity in feet, 32.2 feet per second squared. Quick unit sanity check. Your feet will cancel. You'll be left with root of seconds squared. So that'll be a per seconds in the denominator, which is perfect for theta because it's just going to be radians. So conserving paper here. Just write in the answer. Theta dot 11.35 radians per second, which is about 2 revolutions per second. Let's see how she does. Okay, to analyze, I'm going to drop it to a quarter speed. All right, so let's try to look at a quarter speed, kind of count along to think how long it takes for her to do a complete loop at quarter speed. Oh, this mouse is not working today. You see those little legs working hard. She's building suspense. Come on. 1 1,000, 2 1,000. So, okay. About 2 seconds. About 2 seconds to do a pull. So if it took her about 2 seconds to do a loop, and that was at quarter speed, that means she would do one loop in about a half a second. So 2 revolutions per second when she goes, woo woo. That's about how fast she was moving. Kind of a funny little hamster problem. So if anybody sees a little white hamster in my neighborhood, come let me know. All right. similar problem. This one's not about abusing hamsters. This is like a child abuse one now. So this is the park next to my house. It used to have a merry-go-round. And the little gal with her face obscured, that's my daughter. When she was little, I would start her on this merry-go-round. I'd run, and I'd jump on the outside. She'd be hanging there. And then I'd pull myself from the outside of the merry-go-round to the inside. We will learn in a month, conservation of angular momentum, that, hey, this merry-go-round is going to speed up then. It's going to go from whatever speed I jumped on. When I pull myself to the middle, things are going to go faster. So when it spins faster, instead of her hanging there, she gets kind of chucked to the outside. Not like a projectile motion problem. That's a neighbor kid. That's a different story. Come on now. Got to click happy. All right. So I jump on the outside. It's going pretty slow. Then I pull myself to the middle and it spins, right? Indeed, this kid's got pretty good grip. What you will find is that your nieces and nephews or your neighbor kids might not have quite as strong of a grip. Right, so she's flying out there, and it was a little circus trick. We do it with all the kids. But it got me to thinking, well, one, what kind of forces does she have to have in her arms in order to fly like that, right? Because you think, if I'm hanging just vertical, half my body weight is in each arm, right? But as you're spinning, to force you out like that, I mean, the tension in your arms has to go way up. And if you were flying horizontally, the tension in your arms would be go to infinity. But you got some little angle that's kind of correcting that. So my thought was, can I find omega such that the tension in each arm was equal to her total weight? So you think hanging on a monkey bars, half your weight in each arm. This is equivalent to your full weight in each arm. So hanging on the monkey bars, your twin brother climbs on your back and grabs around you, right? That's the kind of tension we're talking about. So if you saw what happens here, as I pull myself from the outside to the inside, her body position changes. She goes from hanging like this to then hanging out. So there is going to be some change in the radial component as she moves from here to here. There is an angular acceleration. If I was looking top down on this thing, it's going to speed up. But for this problem, we're going to simplify things and we're going to look steady state. So it's not the case, but we're going to assume that as I pull myself in, this merry-go-round then is at that constant angular velocity and just stays there so that we can analyze what's happening. That just allows us to kind of forget about a few different forces to make it a little bit easier. All right, so we'll do top view and a side. All right, so from the top, we're looking at this merry-go-round spinning. There's a little bar where you hang on for dear life. And then there's a little body in a dress that's hanging off there, right? So try to think about what's happening here. This is the radial direction. This is the theta direction. And then coming out of the board would be the z direction. And if I looked at this from the side view, I'd have some merry-go-round. It would be spinning about this point. I don't know why it looks like that. Actually, let's do that. I just drew half a merry-go-round instead. It's spinning around this axis. So my z direction, the bar she's hanging on is out here, and her arms are going this way. And she forms some angle with respect to the Earth. That's going to be key in figuring out how much tension's in her arms. The radius of the merry-go-round is 1 meter, and then to her center of gravity is an extra half a meter. Her mass, it doesn't matter. We'll find out that it drops out, but let's call her 15 kilograms when she was 2 years old. Okay, so get an idea of what the problem looks like. Let's try to translate this to an FBD. I think our side view tells the story the best. So U hat K and U hat R. Now my theta direction is into the page. So acting on her body, mg coming down, and then through her arms, 2t. And some angle theta. Kinetic diagram, mass times acceleration in r, mass times acceleration in z, or k. Oh. We've kind of unpacked the question. We've drawn our free body diagram and kinetic diagram. Now we want to put them to use. Sum of forces in the r direction. Look at my free body diagram. I've got 2t happening in the negative r direction. So minus 2t, and that would be the cosine leg. 2t cos theta equal to m times acceleration in the r direction. Before we leave that, let's just look at acceleration in the r direction. R double dot minus r theta dot, or omega, squared. Okay? We're going to look at this steady state, and that's kind of the assumption we've made to make things a little bit easier. So we're not going to worry about the fact that her center of position is moved to here. We're going to say, now she is spinning at this constant angular velocity. She got there. Her body is hovering in perfectly. So I'm going to say r double dot is 0, and we'll write steady state. So if we redo this, minus 2t cos theta is equal to minus mr theta dot squared. I didn't want to call this theta. I just looked at my solution. I don't want to call that theta because I have a theta direction, right? That's looking at my top view, going clockwise. So I'm going to change this to a phi. Sorry about that. This is now phi. Just so we don't get confused with something I already called theta just a minute ago. You are now phi. Sorry. Okay. So we're going to say that our tension in each arm was mg. We got to think a little bit about our angle here to be able to solve for say, the speed that we're going at, which is what I want to find. So if I need to know something about our position that we're hanging so that we can get this is what we want. And we can get this angle from our other direction. Sum of forces in the z. Positive going up. So jump back to my free body diagram. I've got a positive 2t. Now I'm looking at the sine leg, 2t sine phi, minus an mg, equal to mass times acceleration in z. All right. Our acceleration in the z. This is again going to be 0 from that steady state assumption. We're going to say she's been flying at that position now for a while. She isn't coming up. So we can do that. We know that our tension is equal to mg. We've got some m's. These m's will cancel. These g's, I guess those will cancel. I need to find that sine theta is equal to, when I move all this over, equal to a half. That's not a theta. I'm going to not screw that up. That's still our phi. Sorry. So our angle that we're flying at is 30 degrees. So all I did was I moved some things over. This is a little messy. So 2mg sine phi minus mg is equal to 0. So I went like this. And then I divided and was left over. Okay? So, okay. So now we've got an angle. We've got a tension. We've got a radius. That's 1.5. We can solve for our theta dot. So back to our R equation. Minus 2 mg cosine 30 degrees equal to minus m. My R was 1.5 meters times theta dot squared. M's will cancel. This g will go to 9.81 meters per second squared. The negatives will cancel. In here, I'll get theta dot, which is also omega, is equal to 0.53 hertz. Oh, 0.53 hertz. I shouldn't have written that in hertz. That's just tricking you guys. 3.36 radians per second. Sorry. A hertz is a cycle per second. I'm from the vibrations world, and that's where my brain goes. And this is easier for counting. So half a cycle per second means it takes 2 seconds for her to go all the way around. And if this thing would ever unpause, which is very angry with me today, you kind of can estimate the time it takes for her to do one loop. 1,000, 1,000. About right. If I just counted when she passed that 0 point. So roughly at a cycle every 2 seconds with this kind of geometry, the tension in her poor little skinny arms, not too bad, right? You kind of look at that and you think, that's about 30 degrees. If I drew in what the horizontal was there. So next time you go to a playground with a merry-go-round, they're a dying breed, so take advantage of this. You get the best bang for your buck if you're a big guy and your torture subject's little. And we'll talk about that in a month. But Okay. Oh, man. Okay. This is what I want to show. One more example, and then we'll be done. So there's actually a harder example in these notes, I believe that's hiding there. I'll post a solution to this on the course website. This one's a little sneaky to walk through because you have this ball that's rotating on the hemisphere as it's attached to this connecting rod. And as it rolls at a certain angle, the ball will want to release contact. So it's kind of the same idea of losing contact that we had with sprinkles, where the normal force goes to zero. This one just makes the whole problem a little bit trickier in that you've got to tie these two geometries together. You've got the rotation from this bar, and you've got the radius of your hemisphere. So it's a little ugly. I think unnecessary for us to show it. So I'll post those solutions. We'll do an easy one. All right. We got a snowmobile with a 200 kilogram mass that has a 200 kilogram mass with its passenger, and it's traveling up the hill at a constant speed of 6 meters per second. Determine the resultant normal force and the resultant frictional traction force exerted on the snowmobile at the instant it reaches point A. We're going to treat the snowmobile as a point mass, so we're going to neglect the size of the snowmobile. All right, what do we got? The snowmobile is riding some curve. We're given the shape of this curve. Minus 0.5 times 10 to the negative third x cubed. And we're given x and y. And we want this at some location when x is 10 meters. All right. So our snowmobile, guy's gassing it, flying up the hill. Right? The force coming off of that track onto the snow, that's a static frictional force. So if you think of like, pretend one hand is the snow, pretend your other hand is the track, and as this track is moving, it's not sliding relative to that snow. It's kind of digging into the snow and going. So there's no relative motion between that track and the snow. So that track kind of flops down and then slides over and kind of flops down again, right? That's, we call roll without slip. We're going to spend a whole lot of time on that later. But if you kind of think of it the same as if you're walking. I'm certainly moving relative to the ground, so I have a velocity, but my feet, they're sticking to the ground, right? At that moment they're stepping, it's not going anywhere. Right? And that's the same idea with this friction that's happening on the snowmobile. The friction from my foot to the ground is what's allowing me to propel forward. So, why do I go into that whole spiel? Last time we got together, we talked about friction between two surfaces, and I said, hey, that kinetic friction force, that's going to oppose motion. So you think, the force acting on this body from friction, that's got to oppose motion. But that would be if the body was sliding. So if I was riding my snowmobile and then I hit my snowmobile brakes and that track was sliding relative to the snow. Since we're not in that case, we have static friction. The friction from that belt is actually what's pushing the snowmobile forward. So it's a traction force. So really, I could write it like a thrust. That's what's going to get this snowmobile zipping up the hill. Okay? If that whole walking and looking at my shoes thing didn't jive with you, give me another try in 2 months, okay? We'll talk more and more about that. So what have I got? I got some thrust acting on my snowmobile. I've got mg going down. This is equal to my kinetic diagram. So, you've got options, what you can do here. You think, if I'm feeding you information where you know the shape of that curve that we're riding on, okay, I got a way to convert this shape to a radius of curvature. Right? That was that big equation that we talked about. So this is like leading you towards nt. You were given that your velocity was a constant 6 meters per second. So you're given information for velocity. At constant, v dot is equal to 0. So I've given you all these kind of juicy tidbits of information that are going to make the nt coordinate system your choice. Right? You're given v dot. You're given v. You're given the shape of this curve so you can find rho. All rho's, all signs point to nt. So for nt, now your job is to figure out the directions. U hat t, tangent to the curve. Normal direction pointing towards the center of curvature. So that's going to mirror what you have in your kinetic diagram. M times at, m times an. Oh, I forgot one thing in my diagram here. I forgot the normal force where it's sitting on the snow. I kind of need that normal force because, geez, find the normal force. That's what I'm trying to do in the question. So I want to find N and what I'm calling T as my traction force. All right. So sum of forces N. Sum of forces T in my two directions. Might have to do a little bit of geometry to break these up. But our T direction, our thrust, is happening in the direction of motion, and our N direction is happening in the direction of our normal. You got to break up this guy, mg. Okay? So you're going to have something, something. In the normal direction, mass times v squared over rho. I just shortcutted. This is what an is. And in the tangential direction, mass times v dot, which the problem statement told us was 0. Okay? You've got y as a function of x. Go ahead and calculate rho. That's what we needed. The only other thing in here, this is going to be a function of theta. We got to find theta. Again, I'm leaving this blank. I'll fill that in when I post these. The angle we're traveling, theta, on this slope. This is how we're going to do it. We're going to say the change in x over the change in y is the slope at that point. Kind of sneaky, right? But that's the slope we're riding on. So tangent of theta, opposite over adjacent. dy dx, we have an equation for. We're going to find it at a certain position at 10 meters. We can find theta. Okay. I will complete this, and then I will post it. Thank you for hanging in there a little bit late.